Hey everyone, and welcome to this deep dive. We're going to be taking a look at some really interesting research on LLMs, you know,
Mm,
large language models.
yeah.
And we all know how these models like ChatGPT are super amazing at generating text and all sorts of stuff, like writing poems or code, or even like holding pretty convincing conversations.
Right.
So today, we're going beyond that. We're going to explore their potential for something called text encoding.
Text encoding is basically turning words and sentences into something that computers can actually understand and work with.
Oh, that's a good way to put it.
It's pretty important,
Yeah.
for a lot of tech we use every day.
Yeah, definitely. Like search engines,
Mm-hmm.
when you type something into Google, it has to be able to compare your words to like billions of web pages to find the stuff that's most relevant, right?
Yeah. That comparison totally relies on text encoding.
And it's not just Google. Think about like recommendation systems,
Oh, yeah.
like Netflix suggesting what to watch next based on what you've watched before.
That's text encoding, too.
Exactly.
At its core.
And this has traditionally been the domain of encoder-only models, like the famous BERT model.
Yeah.
But this research paper that we're looking at today, LLM2Vec, large language models are secretly powerful text encoders.
Mm-hmm.
It suggests that these decoders-only LLMs, like ChatGPT, might actually be really good at encoding too,
Yeah.
which is interesting. So we have this research paper. We're going to dive deep into it. But I think before we get into the how, maybe it makes sense to understand why decoder-only LLMs haven't really been the go-to for text encoding. What do you think?
Yeah, I mean, the main reason has to do with how these models process language, They use something called causal attention. So imagine like you're reading a sentence, but you can only look at one word at a time
Uh-huh.
in order, and you can't go back.
Okay.
So, no looking back to reconsider words based on what comes later. That's kind of like what causal attention does. And that's great for generating text word by word, but not so much for capturing the entire context of a sentence, which is like super important for encoding.
Yeah, that makes sense. I guess it's like trying to understand a story without knowing the ending, right?
Exactly.
You might miss out on something.
You'll miss some nuances for sure.
But these decoder-only LLMs,
Yes.
they do have their strengths too, don't they?
Absolutely.
What are some of the advantages?
Well, one of the biggest advantages is what we call sample efficiency. So they learn from every single word they see during training,
Interesting.
not just a small percentage, like traditional encoder models.
Okay.
So they can potentially get way more meaning out of the same amount of data.
And of course, we can't forget their amazing ability to actually follow instructions and adapt to different tasks. Like, I mean, ChatGPT is a perfect example of that.
A good example.
Yeah. So I guess the question then becomes, how do we, like, overcome those limitations of causal attention and unlock the full potential of these powerful models?
Yeah. That's where this LLM2Vec comes in.
Okay, tell me about LLM2Vec.
So the authors of this paper, they present this technique called LLM2Vec that transforms these decoder-only LLMs into like surprisingly powerful text encoders.
And how do they actually do that?
Well, they lay it out in 3 steps, and they've got a nice figure in the paper, figure 1.
Yeah.
The first step is enabling something called bidirectional attention. And that basically gives the LLM the ability to look both backwards and forwards in a sentence at the same time.
So instead of looking at words one by one, it's kind of like having a bird's eye view of the whole sentence?
Yeah, exactly. And they call this bi in the paper for bidirectional.
By, okay. And what's the next step?
The next step is something called masked next token prediction, or MNTP.
Okay.
This is kind of like playing a game of fill in the blanks. So the LLM is presented with a sentence, but some words are hidden. And it has to predict those missing words using both the words before and after the blank.
Oh, so it's not just predicting the next word like it normally would. It's using that bidirectional vision to fill in the gaps.
Exactly. And this MNTP training kind of fine-tunes the LLM's bidirectional skills.
Okay.
It helps it create richer, more contextualized representations of words.
So we've given it this bidirectional vision. We've trained it to fill in the blanks. What's the third step?
The third step is something called unsupervised contrastive learning. And they use a technique called SimCSE for this.
SimCSE.
So imagine you're trying to match socks in the dark. You're feeling around, comparing one sock to another, trying to figure out if they're a pair.
Okay.
SimCSE works in a similar way. The LLM is giving slightly different versions of the same sentence, and it learns to recognize that these variations are similar in meaning while distinguishing them from other unrelated sentences.
It's learning to group similar socks together, so to speak.
Yes, exactly. And through this process, the LLM becomes really good at capturing the overall meaning of sentences, which essentially turns it into a powerful text encoder.
Okay, so just to recap, we take a decoder-only LLM. We give it bidirectional vision with bi. We train it to fill in the blanks using that vision with MTEB. And then we teach it to differentiate between similar and dissimilar sentences with SimCSE.
Yep, that's LLM2Vec in a nutshell.
And this, according to the research, leads to some pretty impressive results.
It does, yeah.
Tell me more about the results.
They put this LLM2Vec to the test, evaluating it on all kinds of tasks.
What did they find?
The results are, as you said, pretty impressive.
Well, let's start with the word-level tasks. They use the LLM2Vec benchmark, right?
Right.
Which includes things like identifying parts of speech.
Right.
Like, is this word a noun, a verb, an adjective, etc. And also name entity recognition, where you're trying to figure out if a word is part of a person's name, a location, that sort of thing.
Mm-hmm.
And for comparison, they used decoder-v3 large, which is a state-of-the-art encoder-only model.
Yeah.
So how did it stack up?
Well, you can see in Figure 2 of the paper, LLM2Vec outperformed the encoder-only baseline by a significant margin on all 3 word-level tasks.
Oh, wow. So it's not just a small improvement.
No, it's quite substantial.
That's really interesting. But those are just word-level tasks.
Right.
What about more challenging sequence-level tasks?
Yeah, the ones where you have to encode the meaning of, like, entire sentences.
Exactly. So what did they do for that?
For that, they used the Massive Text Embeddings Benchmark, or MTEB. It's a collection of 56 different data sets that cover a whole range of tasks that require understanding the meaning of sentences and even paragraphs.
It's like the Olympics of text encoding.
Kind of, yeah.
And to make sure the comparison was fair, they used the same task-specific instructions as previous research on this benchmark. And for pooling, how you go from individual word representations to a single representation for the whole sentence, they tested several methods.
Right, including EOS, mean pooling, and weighted mean pooling.
And they even did an ablation study, which is shown in Figure 3, to show how each component contributes to the overall performance.
Yeah, that's important.
So what were the results on MTEB?
Well, the results were really promising, even without that final SimCSE step. LLM2Vec consistently outperformed the baseline of just using causal attention. And when they added SimCSE, the gains were even more significant, sometimes even exceeding 40% improvement.
Wow, that's huge. But how does this compare to other approaches for turning decoder-only LLMs into encoders? Like echo embeddings, for example.
That's a good question. They actually did compare LLM2Vec to both unsupervised BERT models and echo embeddings. And as you can see in Table 1, LLM2Vec outperforms echo embeddings on several models, including S-Llama 1.3b and Llama 7b.
That's impressive. And it does so much more efficiently, right? Because echo embeddings basically duplicate the input.
Exactly. So they take much longer to process, especially with longer documents.
LLM2Vec gets better or comparable results without that computational overhead.
Making it more practical for real-world stuff.
Yeah, that makes sense. So LLM2Vec seems to be winning in terms of both performance and efficiency. But I'm curious, how does it actually change the way these models understand language? Like, what's going on under the hood?
Well, that's where things get even more interesting. To understand that, the researchers went beyond just looking at the numbers.
Okay, and that's what we'll talk about next time. We'll explore how LLM2Vec affects the internal workings of these models and maybe uncover some surprising insights along the way. So stay tuned for part 2 of our deep dive into LLM2Vec.
Sounds good. So welcome back to our deep dive into LLM2Vec.
Yeah, we're really getting into it now.
To really get how this technique changes things for text encoding.
Yeah.
With these decoder-only LLMs, the researchers, they went beyond just looking at overall performance.
Right. They wanted to know how LLM2Vec actually affects the way these models process and represent language.
Yeah, exactly.
Specifically, they wanted to test if LLM2Vec really helps models use information from future tokens. And that would be a huge deal for decoder-only LLMs because, as we discussed earlier, they've typically been limited by that causal attention.
Yeah. So to test this, they had a clever approach, They created a data set of sentence triples.
Okay, triple.
So you have a query sentence, a positive sentence that's similar in meaning, and a negative sentence that has a different meaning.
Okay.
But here's the thing. All three sentences, they start with the same words, like the same prefix.
Oh, interesting. So it's like they share a beginning.
Yeah, exactly. So the idea is to see, can the model still tell the difference between the positive and negative sentences, even when they start the same way?
I see. So it has to use the context from the entire sentence to figure it out.
Yeah. It can't just rely on the beginning.
Okay, so what did they find?
Well, the results of this analysis, they're shown in Figure 4 for two specific LLMs, SLAM-A 1.3b and Mistral 7b. And what's cool is that for both models, using bidirectional attention and training with MTP, that fill-in-the-blanks thing, led to a really clear separation between the positive and negative examples.
So that means that the models were actually able to use the future context, like the part of the sentence that comes after that shared prefix, to better understand the whole sentence.
Exactly. It really shows how LLM2Vec kind of breaks free from those limitations of causal attention.
Right, so it's not just stuck looking at one word at a time. It can grasp the whole picture.
Yeah, and get that richer understanding of the sentence.
Okay, so that makes sense. But I think you mentioned there was another interesting finding, right? Something unexpected?
Yeah, there was.
Tell me about that.
So Mistral 7b, one of the LLMs they tested, it seemed to handle the bidirectional attention surprisingly well, even without any MNTP training.
Wow, so it was doing well on this task,
Yeah.
even without that second step of LLM2Vec.
Yeah, it was almost like this model already knew how to kind of look ahead in a sentence.
That's really unexpected.
It was. And the researchers were, curious about this result, so they dug a little deeper. They wanted to analyze how bidirectional attention impacts the internal representations of these different models.
Internal representations, you mean like how the model sees each word.
Exactly,
So,
how it encodes it. They wanted to see how, turning on this bidirectional attention changed those representations, even without any extra training.
okay.
So the expectation was that, just enabling bidirectional attention without actually training the model on it would change those representations a lot, because the model wasn't really taught how to deal with this new way of processing information, right?
Right, that makes sense.
And for SLAMAPO 1.3b and LLAMAPO 2.7b, that's exactly what they saw.
And that's shown in Figure 5.
Yes. Figure 5 shows that for those models, enabling bidirectional attention led to really low similarity between the representations it generated with causal attention versus with bidirectional attention. So that means, the model's understanding of each word changed quite a bit when it was allowed to look ahead in the sentence.
Okay. But with Mistral 7b, things were different.
Yeah. With Mistral 7b, something pretty remarkable happened. The representations, they stayed very similar, like high cosine similarity across most layers and word positions. You can see it in Figure 5.
So even though Mistral 7b hadn't been trained specifically to handle bidirectional attention, it was already doing something similar internally.
That's right, it was. And this finding, it led the researchers to think that maybe Mistral 7b had actually been exposed to some kind of bidirectional training during its initial pre-training. They suggest that maybe it was trained using something called prefix language modeling, and that could explain this unusual ability.
Interesting. So it's like Mistral 7b had this kind of head start in understanding the whole sentence, even before they fine-tuned it with LLM2Vec.
Yeah, exactly.
That's fascinating.
It is. It really reinforces the idea that decoder-only LLMs have this potential for text encoding. Like, we're just starting to see what they can do.
Right. Okay, so we've seen how LLM2Vec can improve performance on all these different tasks. And we've seen how it can actually change how these models understand language, right?
Mm-hmm.
But the researchers, they didn't stop there. They took it a step further.
They did. They also looked at how LLM2Vec interacts with supervised contrastive learning.
Ah, okay. So up until now, we've been talking mostly about unsupervised learning, where the model learns from unlabeled data.
Right. But with supervised learning, we actually have labeled examples to guide the model's learning.
Okay.
And supervised contrastive learning, that's a specific technique that uses labeled data to train models to tell the difference between similar and dissimilar examples.
Okay.
So the researchers wanted to see, could combining LLM2Vec with supervised contrastive learning make these decoder-only LLMs even better?
Okay, so they took LLM2Vec and, applied it in the supervised setting.
Yeah. They used this massive data set called E5.
E5.
Yeah, it combines several popular text embedding data sets, and this allowed them to really evaluate LLM2Vec's effectiveness in a supervised setting with lots and lots of labeled data.
And what did they find? Did combining LLM2Vec with supervised learning, actually lead to better results?
It did. The results, you can find them in Table 2 of the paper.
Oh.
And for all the models they tested, LLM2Vec, Even without that SimCSE step, it gave a big performance boost, like compared to just using causal attention with weighted mean pooling.
So even in the supervised setting, just enabling bidirectional attention and using that MTEB training, that really helped these models with text encoding.
Exactly.
Wow. But I think you said the most interesting finding from the supervised evaluation was about sample efficiency.
Yeah, that was a big one.
So remind me, sample efficiency means the model can learn effectively from less labeled data, right?
Exactly. So to show this, they tracked the performance of different models throughout the training process, saving checkpoints every 25 steps and then evaluating them on that 15 tasks MTEB subset.
Gotcha. And that's shown in Figure 6.
Yep, figure 6. It shows that the LLM2Vec models, they consistently got better performance earlier on in training compared to models trained with just causal attention.
So they're basically learning faster.
Yeah, and more effectively from that labeled data.
Okay, that makes sense. So LLM2Vec not only boosts performance, it also makes the training process way more efficient.
Exactly.
That's pretty amazing.
It is. And that's really important in the world of large language models where, training can take a ton of time and resources.
Right, it can be pretty intense.
Yeah. So LLM2Vec offers a way to get that high performance with less data and less training time.
That opens up a lot of possibilities. Well, we've covered a lot of ground in this deep dive into LLM2Vec. We've talked about the 3 key steps, the impressive performance on different tasks, and even how it changes the way these models understand language.
We've looked at how it works with supervised contrastive learning and its amazing sample efficiency.
Right. This research is really exciting. It kind of changes what we thought was possible with decoder-only LLMs for text encoding.
I agree.
And I think in the final part of this deep dive, we should take a step back and, think about some of the bigger implications of this research.
Sounds good.
Okay, so we're back for the final part of our LLM2Vec deep dive. We've seen how it works, those 3 steps, BAE, MNTP, SimCSE, the impressive results on benchmarks like Encoders 2003 and MTEB. We even looked at the analysis, how it changes how these models understand language.
Yeah, and how LLM2Vec works with supervised contrastive learning, how it does on that E5 dataset, and that crazy sample efficiency like we saw in Figure 6.
Right. So I guess as we wrap up here, I think it's worth pointing out what makes this research so important. For a long time, people thought decoder-only LLMs just weren't good for text encoding because of that causal attention thing, right?
Yeah.
But this research really changes that. It shows that with a few tweaks, like the ones they talk about in this LM2Vec paper, these models can be incredibly powerful encoders.
Yeah.
And even, beat those specialized encoder-only models in some cases.
It's like we unlocked this hidden potential.
Yeah, exactly. And that's what makes it so exciting. It opens up so many possibilities for text encoding.
Yeah, definitely.
Well, this has been a really cool deep dive. We learned a ton about LLM2Vec, how it works, its strengths, its potential. Thanks for joining us.
It's been fun.